Okay, so this video is going to be an introduction to z-scores. And a z-score is a ratio that can be used to determine how many standard deviations a value lies from its mean by taking into account a measure of spread, which in this case is a standard deviation, which is shown right here. And it also takes the mean. So the individual value minus the mean divided by the standard deviation. And z just tells you how many standard deviations it is away from the mean. So if it's a positive z-score, we're this many standard deviations above the mean. If it's a negative z-score, it's this many standard deviations below the mean. One thing I want to tell you about this is if you multiply if you multiply the values by a constant, the z-score doesn't change. If you add constants, z-scores don't change. So transformations do not change z-scores. Transformations do not change z-scores. That's important to note because remember, if we add a constant, measures of center change, but spread doesn't. If we multiply by a constant, measures of center and spread change. But when it comes to z-scores, we multiply by the values by a constant, the z-score doesn't change. We add a constant, the z-score doesn't change. So z-scores do not change. So this is our basic z-score formula, and this is what we're going to be working with the time being. We'll later make it a little more challenging when we talk about central limit theorem, but that's a ways away. When we talk about central limit theorem, we're going to adjust, because we're talking about means, we have to adjust for the sample size, all right? But for the time being, we're going to be talking about individual scores. And with an individual score, this is what the z-score formula is. All right. So it's a ruler that we can use to compare different distributions. That's pretty cool. So in other words, I can use it to compare ACT scores to SAT scores, although their center is different because the center for an SAT is around 1,000. I don't remember the center of the ACT. They have different standard deviations, but I can make that adjustment because with a z-score to make comparisons. And we're going to take a look at it in this example here. So at a college, the scores on the chemistry final exam are approximately normally distributed with a mean of 75 and a standard deviation of 12. So they're telling me, and I'm going to do this off on a separate sheet of paper and then show it to you in a moment. So on the chem, here's what they're telling me. It has a mean of 75 and a standard deviation of 12. The scores on a calculus final are also normally distributed with a mean of 80. So this is on the calc. And they have a mean of 80 and a standard deviation of 8. So we can sit there and say, hey, they have different centers. Chemistry is lower, but has greater spread. This is higher, but has less spread than the chemistry. A student scored an 81 on the chemistry final. So they scored the X value, their score was an 81, and it scored an 84 on the calculus final. Relative to the students in each class, in which subject did the student perform better? So in this case, let's do this. Let's find out, calculate the z-score. Z equals X minus mu over sigma. For chemistry, we're going to have 81 minus the 75 divided by 12. And 81 minus 75 is 6 over 12. So we end up with a z-score of 0.5. It's positive. So on average, he scored a half standard deviation above the average. And we look at this and we go, you know what? Sure enough, his score is above the average, and the standard deviation in this case was 12, and he scored a half standard deviation or 6 points above it. So that makes sense. How did he do on the calculus? Well, z equals X minus mu over sigma. And by the way, if they talk about z-scores, I write the formula down. If they talk about normal, anytime they talk about z-scores and normal, I write this down and I start plugging in. So then I go, my X value happened to be an 84 minus 80 divided by 8. So Z equals 84 minus 80 is 4. So I end up with 4 over 8. So I end up with a Z equal to 0.5. So he scored a half standard deviation above the average. Well, that means relative to the students in the course, he scored equally well on both exams. All right. The student scored a half standard deviation above the class for both exams, which means the student performed equally well on the 2 exams relative to the other students. So the next question is, what would a 60 on the chemistry final equate to the calculus final? It's like, well, I need to back up just a bit. On the chemistry final, the mean was a 75 and the standard deviation was 12. And he was saying, what would a 60? So in this case, it's like, how did they score on the chemistry final? Well, once again, Z equals X minus mu over the standard deviation. He scored a 60. 60 minus 75 divided by 12. So we scored 15 points below the average. And if I take 15 and divide it by 12, I find out that, and by the way, this is a negative 15. So in this case, Z equals a negative 1.25. So he's 1.25 standard deviations below the average on the chemistry final. But I want to know how that compares to the calculus final. Well, the calculus had a mean of 80 and a standard deviation of 8. Well, we know that he has to be 1.25 standard deviation. So we know that below, so he's going to be below an 80. But how much below? Well, I can sit there and go, you know what? On the calculus final, again, Z equals X minus mu over sigma. And this time I'm looking for that X value because I want to know what it would be that he scored that was equivalent to that 60. Well, we don't know the X, we're looking for that, but I know that the mean on the calculus final happens to be 80. And I know the standard deviation is 8. And I know that I need an equivalent Z score, which is negative 1.25. So when I go through some algebra here, and be careful with your algebra, 8 times a negative 1.25. This is negative 10 equals X minus 80. So I add 80 to both sides, and I end up with 70. So 70 equals X. So a 70 on the calculus final would be equal to a 60 on the chemistry final relative to the other students. The 70 is 1.25 standard deviations below the mean, and the 60 is 1.25 standard deviations below the mean. And by the way, just so you know, in college, a lot of times there are curves, and a lot of times these curves are made based on things like that, okay? And there's obviously curves on the SAT, et cetera, and they're made this way as well. The table below describes the distribution of median household incomes in the 50 states. So basically we're talking about median income. So the median income happens to be 50,000. Find and interpret the Z-score for North Carolina that has a median income of 41. So, and I said median, I should have said mean. All right, so this should have been based on the mean. I apologize, because this is why the mean is part of the formula, not the median. So X minus mu, so 41,553 minus this, because my standard deviation is here, and I end up getting negative 1.24. So the mean income is 1.24 standard deviations below the national mean. On average, North Carolina has a mean income 1.24 standard deviations below the national. And we go, yeah, 41,000 is definitely below 51,000. And how much below? It's 1.24 standard deviations. All right, now they tell New Jersey has a standardized score of 1.82. Well, that's positive. So they want us to calculate, and it says median, and we're going to calculate the mean. All right. Well, if it's positive, that means we're going to expect to have a mean income above the national average. So we're looking to find this value right here. So my standard deviation, 8,210, there's my mean. And when I solve it by algebra, this times this, and then adding the 51,000, I end up getting 66,685. So New Jersey's mean income is 1.82 standard deviations above the national mean income. All right. So New Jersey's mean income is 1.82 standard deviations above the national mean income. So that's an introduction to into z-scores. We'll have more z-score information or more z-score practice in the next video.